Probability is an important topic in statistics. Statistics is not an exact science, which means that what we really want to do is to minimize the chance of having a conclusion be false because of bias, and we want to maximize the chance of our conclusions being correct. So there's a lot of probabilities involved in statistics. We want to go ahead and start with some of the fundamentals. Starting with the theoretical probability. The probability of an event is a way of quantifying our chances. So it's the number of favorable outcomes divided by the total number of outcomes. For example, if you flip a single coin, what's the probability of getting heads? Well, we've got a coin here, and there are two possible outcomes. We call this the set of possible outcomes, the sample space. So H, T. So the number of favorable outcomes would be 1, and that would be heads, over the total number of outcomes, which is the number in my sample space, and that's 2. So we could describe that as 1/2, or we could use the decimal 0.5, or we could use the percentage form of that, 50%. Number 2, let's say that we flip 2 coins. If we're flipping 2 coins, that means we've got more possibilities. I'm going to set up a tree diagram for this one. So for the first coin that we toss, we've got a result of either heads or tails. For the second coin, we can follow heads with a heads or tails on the second coin, or we could follow tails with a heads or a tails. This gives me a sample space, and I can follow this as I move through my tree diagram. So heads and heads would be an outcome for those 2 coins. Heads on the first, tails on the second. Tails on the first, that's this one. Tails on the first, heads on the second, and then tails on both. The number in that sample space, n, which is the same n that we've used in other parts of statistics, is the total, is equal to 4. Okay, so that's our sample space. So I'm just going to say see below. So we've got our sample space. We want to know, what is the probability of getting 2 heads? Well, I can go through my sample space and find that case. There it is, 2 heads. There's one of those out of 4. So 1/4 or 0.25, 25%, 3 different ways to express these probabilities. Now the probability of getting at least 1 head. Well, I want to go through and I want to circle all of those possibilities. So at least 1 head, that would include the outcomes that have a single head in it, or the one that has 2. The only one it doesn't include is the one with 2 tails. So there are 3 favorable outcomes here. So 3 out of the 4, which would be 75%. Okay, finally, we have the probability of an elbow. So, well, there isn't an elbow, right? There's only heads or tails. So this would be 0. Okay, so probabilities, I put that in there because a probability can only be a number between 0 and 1. So probability less than or equal to 1. And that would be in either the decimal form. Did I do 0.25 and 25%? 0.25, either the decimal form or the fraction. For percentages, it would be between, so the percent probability would be between 0 and 100%. So when we're at the 1 and 100, that means it's a certain outcome. It will, without a doubt, happen. And if we have a 0 probability, it means that it will not happen. So our probability is anywhere in between. Okay. Number 3, let's go ahead and toss 3 coins. So I want to state the sample space. That's a lot to write down and just to kind of come up with. So I'm going to do the same thing that I did up above. So I've got 3 coins now. So first coin, heads or tails. I follow that with the second coin, heads or tails. After tails, heads or tails. And then I follow that with the third coin. And then heads or tails again. Heads or tails again. Oh my goodness, heads or tails. Just enough room. Heads or tails. Each of these, let me grab this one. So each of these lines gets me to one of my outcomes. So I can follow this. So I get one outcome there, all heads. Here's another outcome, heads, heads, and tails, and so on. So I get 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. I'm actually not going to list all of these. Instead, you can just see the tree diagram. But I will say that the number in that sample space is equal to 8. We can also use a multiplication principle to get to these 8. So notice each outcome has 2 possibilities, or each coin has 2 possibilities. So the first coin, so I'll do it here. So the first coin has 2 possibilities. The second has 2, and the third coin has 2 possibilities. So if we're looking at these 3 coins being flipped together, we have 2 possibilities for the first, and 2 for the second, and 2 for the third, and we multiply those together to come up with 8. So this is our multiplication principle. We want to know what the probability is of getting all tails. Okay, so that one's not too bad. That guy is over here. There is one of these. So one of these outcomes out of my 8. 1 out of 8. I could put that into a calculator to come up with the decimal or with the percentage form. What's the probability that they're not all tails? So really, I want everything except the one that I've circled there in yellow. So I can use a complement instead. 1 is the probability of everything, all possible outcomes, minus the probability that I don't want, and that would be all tails. So this is going to be 1 minus 1/8, which would be 7/8. This isn't a bad one to count up, right? You could also count it up. 1, 2, 3, 4, 5, 6, 7 possibilities that don't include all 3 tails. Okay, number 4. Now we're going to flip 5 coins. I am not going to do the tree diagram for this one, but I do need to know all heads. Okay, so probability all heads. I do need to know the number of favorable outcomes. There's only one of those. Every single coin has to land on the heads. What I really need to get my hands on here is the number of favorable outcomes. Oh, not favorable, total. Favorables on top. The total number of outcomes. And I'm going to use my multiplication principle to do this. So the number in my sample space, I have 5 coins. 1, 2, 3, 4, 5. 2 outcomes on the first, 2 on the second, heads or tails, right, each time. 2 on the third, the fourth, and the fifth. So we end up with 2 to the 5th power, which is going to be 8 times 4, or what would that be, 32? Or 32. And I can check that with the calculator. But this is a great way to do our probability. So 2 to the 5th power, and we end up with 32. I had also talked about doing the fraction. So while I'm here, so 1 divided by 8, I can come up with the fraction form of these as well as the decimal form. Okay, so my answer then is 1 out of 32. So I'll do 1 out of 32, so we can express that also as a decimal. So my probability is 1 out of 32. Let me erase this. I have a little more room. So 1 out of 32, which is, as a decimal, let me grab that calculator again. So as a decimal, it's 0.03125. If I move the decimal place twice, it's 3.125%. So a fairly small probability. So 3.125%. Okay, now we've got a spinner. We'll do the dice here in a second. So with a spinner, we want to answer some questions with a single spin. So again, we're looking at the number of favorable outcomes over the total number of outcomes. Another way of expressing this is by saying X is favorable, N is total. So the probability of an even number. There's several even numbers, right? There's 2, 4, 6, and 8. That gives me 4 favorable outcomes out of the 8. I do want to reduce that fraction, so we could say 1/2 or 50%. The probability of getting a 2 or a 7. So here's a 2 or a 7. Either one of those is favorable. So I'm counting up my favorable outcomes. There are 2 of them out of the 8, and this reduces to 1/4 or 25%. Next, we want not a 3. So I just want to take everybody except that 3, which leaves me with 7 numbers. So this one is 7 out of 8. And then finally, the probability of getting an 8 is 1 out of 8. Okay, so favorable out of total. In number 6, instead of doing a single event, we're going to combine events. We're going to roll 2 dice. I want to know the probability of rolling 2 3s. Now, I could set this up as a tree diagram. So I would have the first dice and then the second. 1, 2, 3, 4, 5, 6. And then on the second, I would follow a 1 with a 1, 2, 3, 4, 5, or 6. And a 2 with a 1, 2, 3, 4, 5, or 6. That's a lot of work, right? And it's only 2 dice. So instead, I'm going to use my multiplication principle to come up with my total number of outcomes. So N, I've got the first dice, and I use that multiplication for the and the second dice. 6 possible outcomes on the first dice, and 6 possible outcomes on the second dice. So we get 36 possible outcomes. I want to roll 2 3s. So as I put this together, to get 2 3s, there's only one group of 2 3s. So this would be 1 out of 36. I can also break this down into a probability with and 3 and a 3. This will do the multiplication principle for the outcomes at the same time. The probability of getting 1 3 is 1 out of 6. And so I multiply those together. The probability of getting a second 3 is 1 out of 6. So we end up with that 136, which is kind of hard to read. That says 136th for our answer. So a couple of ways to break down these events that have these compound events that have a couple of different events combined. Now I want to know the probability that the sum of the die is 5. So I know that I'm going to end up with 36 as my denominator. So I know that. So out of 36, I need to come up with all of the different ways that I can get a sum of 5. So I'm going to do the first die and the second, and I'm just going to set it up this way. So to add up to 5, I could get a 1 on the first and a 4 on the second. I could also get a 4 on the first and a 1 on the second. We think of these as 2 separate events. I could also do a 2 and a 3. So I could do a 2 on the first, 3 on the second, 3 and a 2. 6 won't work, 1 won't. I think that's it, right? So I've got 4 possibilities. So I end up with 4 out of 36, which you can reduce, but your calculator will reduce this also. So let me grab the calculator. I'm going to clear what I had. I'm going to go 4 divided by 36. If you wanted the decimal form, we just hit enter right here, and we get repeating ones, 0.11111, which tells me it's 1/9. But if instead you wanted the reduced fraction, you can go 4 divided by 36, go to the math menu here right underneath alpha. So I hit math, convert to fraction is the second choice. Actually, it's the first choice up there. I'll hit enter, and it puts this as a reduced fraction. Isn't that nice? So my answer would be 1/9 as a reduced fraction. So 1/9 as a reduced fraction, about 11%. Let's do the probability of getting doubles. So as I'm looking at the probability of getting doubles, I can do a similar analysis, and I can do the first dice and the second dice. I can get double 1s, double 2s, double 3s, 4s, 5s, and 6s. So however you think through this, there are 6 different pairs that give me doubles. So this is going to be 6 out of the 36 possible outcomes, and this is going to reduce 2, and you could let your calculator do it. That reduces to 1/6. So we've got that answer there. I'll put a box around it so you can see it through all of my work. The next one, we are using a survey result. I actually looked this one up. So this is from the National Bureau of Labor and Statistics. I think the actual percentage was 69.7, so very close to 70%. So about 70% of high school seniors continue on to some sort of college in the fall. If you randomly meet 3 seniors, what is the probability that all 3 are going to college? So the probability that all 3 would be the probability of college and college and college. That and is my multiplication. So I've got the first person and the second person and the third person. They have the same probability. If I know that 70% of high school seniors continue on to college, that means one person at random has a 70% chance. So I'm going to put 0.7 for the first person, 0.7 for the second person, 0.7 for the third. So that would be 0.7 to the third power. And if I multiply that on my calculator, 0.7 caret above the division to the third, I get 0.343. So about 34.3%. So 34.3%. The events that we looked at up above here in 6 and 7 were independent events. So the probability of the first person going to college did not affect the probability of the second person going to college. Same with rolling the 2 dice. The outcome on the first dice had no bearing whatsoever on the outcome for the second dice. These are independent events. But we have many probabilities that are based on dependent events, where whatever happens to the first event has an impact on what happens in the second event. Okay, so here's an example. There are, this is not the jar, so let me scroll down. There are 10 M&Ms in a jar. 6 of them are red and 4 are green. So just thinking about the probability that we need to compute here, n is equal to 10. It's my total number of outcomes. If Sandy chooses one at random, eats it, then chooses another, what is the probability that they were both red? So I want to do the probability of red and red. I know I'm going to get a multiplication in there. So for the first red, I've got 6 of them are red out of the 10. So this is going to be 6 out of 10. But we take one of those. Actually, I'm going to draw them. Well, kind of. 1, 2, 3, 4, 5, 6, and then we had 4 green, right? 1, 2, 3, 4. Luckily, they're M&Ms. I can draw that. Okay, so Sandy picks one. She eats it, so it's gone, and then she wants to select another one. So I assume the first one was red. Otherwise, this probability theoretically doesn't make any sense, right? I'm looking for favorable outcomes. So 6 out of 10 would be the probability for the first favorable outcome. If that one was favorable, if it was red, that leaves me with 1, 2, 3, 4, 5 left. But it also changed how many M&Ms I have left. I only have 1, 2, 3, 4, 5, 6, 7, 8, 9 M&Ms left. So I've got 6 over 10 times 5 over 9. Notice how I'm counting down. 6 goes to 5, 10 goes to 9. What happens to the first draw changes the numbers in the second draw. Putting this into my calculator, I'm going to use parentheses for the probability of each of those draws, or each of the M&Ms, so 6/10 times 5/9. And I end up with 33.3%. So 33.3%, or 1/3, right? 1 out of 3. What's the probability that they were both green? Okay, so instead, let me grab my eraser here. So instead, we're going to select a green M&M. I need that probability to work out. So the probability of green and green would be, we assume that the first one she draws is green. There are 4 to begin with, out of 10 to begin with, but she takes one and eats it. So that one is gone. So I want the second one to be green also. So green and green, I'm going to multiply that. There are 3 greens left. but only 9 M&Ms left. Okay, let's multiply this together using my parentheses. 4 over 10 times 3 over 9. I'm going to do reduced to fraction here just to remind you. So math, enter, we'll change that to a reduced fraction and we get 2/15. If you wanted that instead as a decimal, you can hit enter again. Oh, actually, I'm just going to type it in again. Just gave me the same number, 2/15, so 0.1333, so 13.3%. Okay, now we're going to use this jar. It's very similar. This time we've got 7 red, 10 green, and 3 blue marbles. So we need N. N is equal to all the marbles in this jar, 7 plus 10 plus 3. That's going to be 20 total. You're going to draw 2 marbles without replacement. This is the same as Sandy eating one, so there's one gone. We're just not going to replace it. We're not going to eat the marble. Okay, so we have the probability that they're both blue. So probability blue and blue. So I start with everything in the jar. There are 3 blues out of 20 total. We have taken one of those away. Okay, so that guy is gone. So now I want to grab another blue. So I go in to grab another blue. There are only 2 left. So blue and blue, I multiply that. And I've taken a marble away, so there are only 19 marbles left. So I've got 3/20 times 2/19. Really nice pattern with these dependent events. If I multiply those together, 3/20 times 2/19. And I end up with 0.01578. So we'll call that about 1.6%. Watch and see how you should be rounding these. So 1.6%. Okay, so now I want to know what's the probability that the first one is blue and the second one is green. Let me get rid of my X's here. So I want the first one to be blue. So the probability of blue for the first and green for the second. Okay, so the first one is the same, actually. There are 3 greens out of the 20, so 3 out of 20. I am going to get rid of a blue this time. So for the second one, I've got all of the greens still in there. And the greens consisted of 10. All 10 are still in there. But I only have 19 marbles left. So for this one, I've got 3/20 times 10/19. So parentheses, 3/20. Just a really nice pattern. 10, all greens were there though, but 19, we did reduce the number of marbles by 1. So about 7.9%. So 7.9%, just about an 8% chance. Now we want to do the probability of choosing 2 of the same color. So we know that we've got 7 red, 10 green, so 10 green, and 3 that are blue. So when we're doing these probabilities, we want to do the probability of red and red, or green and green, or blue and blue. Because I've got cases here, I'm going to end up adding all of these favorable outcomes together. So I'm going to break it down into 3 different cases and then add each of those probabilities together. So as we do the red and red first, we've got 7 of the red. So when I go and draw first red, it's going to be 7 out of the 20. So I've drawn 1 red, that means there's 6 left. So there's 6 reds left and there's 19 marbles left. Now to this, I'm going to add the green case. So now I go back to the entire jar. So I've got 20 in the entire jar. All 10 greens are there, so that's going to be 10 out of 20. But now I've drawn a green, so I multiply that by the 9 greens that are left out of the 19 marbles that are left. So there's my green and green, and then finally the blue and blue. So again, back to the full jar of marbles. There are 3 blue marbles in there, so 3 out of the 20 are blue. And then that leaves me, if I draw 1, there are 2 left out of the 19. So I'm going to go ahead and multiply this together. Notice that there's a 20 times 19 in each of the denominators. So I'm going to go ahead and pull that out as I multiply all of this together. So let me move my calculator over here so we can see everything, and then I'll clear what I've got here. So in the parentheses, I'm just going to put my numerator in. So that's going to be 7 times 6 plus 10 times 9 plus 3 times 2. So there's my numerator, and then I'm going to divide all of this by 20 times 19. So this gives me my probability, which would be 0.363, but we can also write that as 0.36 or 36.3%. So let's write that here as 36.3%. Next, we're going to work with a deck of cards. If you are not familiar with a deck of cards, that's no big deal. I've got a deck of cards provided here. There's also going to be one posted to our classroom. So just, make sure that you've got one that you can refer to if you're not familiar. In the deck of cards, though, you'll notice that half of the cards are red and half of the cards are black. There are 52 cards total, so 52 total. Of those, 26 are red and 26 are black. You'll also notice that there are 4 suits. The first row are the spades. They're a black suit. The hearts, a red suit. The diamonds, I'm just going to abbreviate, and the clubs. These, the jack, the queen, and the king, are all considered our face cards. It's really all you need to know to be able to do these probabilities. So if we draw a single card, I want to know what the probability is that it's red. So we're going to be using our favorable out of total outcomes here. There are 26 red cards and 52 total. That's half the deck. So 1/2 or 50%. The probability that it's 8. Here are my 8s. There are 4 8s. 4 8s out of the 52 cards. So 4 out of 52. I'm going to let my calculator simplify this. I think it's going to be 1/13. So 4 out of 52. Math, convert to fraction. Yay, 1/13. We could also do that as a decimal, of course. Okay, 1/13. The probability of getting a heart, there are all of these. So in each suit, there are 13 cards in each. 52 cards divided into 4 suits. So the probability of getting a heart is going to be 13 out of 52. That's also 1/4 of the deck. So 1/4 or 25%. Next, I want to know the probability of getting a 2 or a club. Let me erase some of what I've got here. A 2 or a club, and I'm going to grab a different color pen here. Grab yellow. Okay, so all of the clubs are down here at the bottom. So if I circle these in yellow, they're there, right? It's the entire suit, so there's 13 there. If I circle all of the 2s, they're here. There are 4 of them, but you'll notice that this 2 of clubs got circled twice, so I actually need to take that one out. So as I put my favorable outcomes together, black, my favorable outcomes, I've got 13 clubs. I have 4 2s, but I double counted the 2 of clubs, so I need to subtract that. And this is all out of 52. So it'd be 17 minus 1, so 16 out of 52. Let's let the calculator reduce that for us. So 16 out of 52. Math, convert to fraction, 4/13. And if I do this as a decimal as well, we get 30.8%, 4/13. 4/13. Okay, so there's that one. Okay, next we're going to draw 2 cards without replacement. So this is similar to the marbles that we drew up above. So these are dependent. What happens to the first card changes the probability of the second card. So these are dependent, if you can read that, dependent events. I want to know the probability that they're both red. So this is probability red and red. There's that multiplication rule. The probability that the first one is red, there are, well, it's half the deck, right? So there are 26 out of 52 cards. But to get this theoretical probability to work out, I have to assume that I actually drew a red card. So I'm going to cross a red card off. So I've drawn a red card, red, and need to assume that the second card is red as well. There were 26 of those. Now there's 25 left. That card that I drew, I set aside, which means that there are also 51 cards left. So very similar to what we saw in the last problem. So let's multiply this out. Parentheses, 26 times 52 and 25 times 51. I think I did not do divide. Let me try that again. Notice how I'm just arrowing up instead of retyping everything. If you can't arrow up, do second and then enter. I did not want times there, did I? I wanted divided by. So I'm just going to edit these. Divided by, much better. So 24.5%. And you could also do that as a reduced fraction, depending on what problem you were working on. So 24.5%. Make sure I got that right. 24.5. Okay, so now let's do the probability that they are both queens. So I want to do probability queen and queen. Queen and queen. Well, there are 4 queens. So here they are. There are 4 queens to start with, 52 total. But I'm going to choose one of these queens. It doesn't matter which one, so I'll choose that guy. So I want my second one to be a queen too. Again, favorable outcomes. So I'm going to draw 3. There are 3 queens to pick from now. But I got rid of that first queen, which means that there are only 51 cards to draw from. Put this into my calculator. Dependent events. 4 divided by 52 times, that means we had 3 queens left and 51 cards left. Enter. Pretty small probability. So that's going to be 0.0045. If I move that 2 decimal places, that is 0.5%. So 0.5%. So a very small probability of coming up with 2 queens.